Well, hello class.
Hi.
Wow. Okay. Use the idea of elimination as if we were just solving a regular system of equations to solve this system. And remember how elimination works. You try to eliminate a variable in one of the equations so you come down to just one variable. But I don't know if you noticed, this is the same example as our example 1. So we've already got the first part done. We've already got it written in operator notation. Well, here's the thing. We're going to apply d minus 4 to the top equation, this one, and we're going to apply negative d to the bottom equation, that's this one, and I want you to see if you can see what will happen when we add those together. It will eliminate the y. See, if we have a d minus 4 and a d applied to y here, and a d minus 4 applied to y here, and we actually this one would be negative d and a d minus 4 applied to y, and we add them together, the y's are all gone, and we're going to have differential operators applying to x only, and we already know, remember, we already know how to solve that kind. So let's go about that. Here it is. Here's the top one with d minus 4 applied to it. Here's the bottom one with negative d applied to it. When we add them together, you should be able to see easily that the y's eliminate. And then we got all this big messy thing applied to x. So if you multiplied this out and multiplied this out and added them together, you would get, trust me, d cubed minus 5d squared plus 4d minus 20. You see the minus 20? This times this. Do you see the let me see, the 5d squared, negative 5d squared? There's one of them. And there's 4 of them right there for this times this, right? So that's negative 5d squared. How many d's? 4, no, 5d from here and negative d from here. So 4d. And you can see where the minus 20 is, and hopefully you can see where the d cubed is. So, aha, that's all it is. It's just this long set of annihilators, sorry, differential operators, applied to x. All right. That's very nice, because that factors, notice it almost looks like the original, but it isn't. D minus 5 times d squared plus 4 of x equals 0. That means we know from this annihilator that c1 times e to the 5t, see? D minus 5, e to the 5t. Look it up in the last section. D squared plus 4 is the annihilator of a constant times sine of 2t plus any constant times cosine of 2t. So we have got x. We've got our solution x, which is a kind of a wonderful thing.
Come on!
Okay, well, we're not done yet. We're going to apply d squared plus 5 to the bottom equation, that's this one, and negative of d plus 1 to the top equation, that's this one, and by doing that, we're going to eliminate x when we add them together. So here they are with that applied thing, right? Here's negative d minus 1 applied to the top equation. Here's d squared plus 5 applied to the bottom equation. And here they are when they're added together. Look, it's d squared plus 5 times d minus 4 applied to y minus d plus 1 times d applied to y equals 0. In other words, d cubed minus 5d squared plus 4d minus 20 applied to y equals 0. And of course, that factors, by the way, if you don't know how to factor that, use grouping. And so we wind up with c4 e to the 5t plus c5 sine of 2t plus c6 cosine of 2t. These c's are different from these c's up here, and that is where the problem lies, because I would like you to go back and look at the original equation. We got a second order in x, first order in y. So therefore we need 3 constants. How many do we have? We have 6. Problem. Problem. Problem.
Come on!
Okay, we're not going to give up. It has too many constants. There should be but 3. So how many should there be? 3. Okay, how do we rectify this? We need to substitute our solutions into the original equation. And find relationships between the constants to come down to 3. So, going back to the original equation in operator notation, remember this one? Let's do the easy one first, okay? I'm not as dumb as I look. So we're into the easy one here, this equation, and we're going to substitute this applied to x, d1 applied to x. See, here's x, here's y, d minus 4 applied to y. See, so let's see what we come up with, and we know it equals 0. That's handy. That's really nice to know. So looking on the left side, d plus 1 applied to c1 e to the 5t. Of course, the derivative is 5c1 e to the 5t, and then plus c1 e to the 5t. But notice over here, we apply d to this term with the e to the 5t. We're going to get 5c4 e to the 5t, and then but minus 4c4 e to the 5t. And we know that's equal to 0. Well, great. Let's divide out the e to the 5t. That's gone. So we've got this relationship. 5c1 plus c1, so that's 6c1s. Plus 5c4 minus 4c4, that's 1c4. 6c1s plus c4 equals 0, so c4 equals negative 6 times c1. We're getting somewhere.
Come on, come on.
Okay, we're not done. That was just looking at the terms for e to the 5t. What do you think we're going to do next? Let's look at the terms with the trig part. So, derivative applied to c2 sine of 2t is 2c2 cosine of 2t. The derivative applied to c3 cosine of 2t is, oh, I'm sorry, I didn't do the 1 yet. 1 times this is just this, right? And now we'll do the d applied to this one, which would be, you see, negative 2 actually, c3 cosine of 2t. And then the 1 applied to it is just it itself, okay? And now we're going to look at this one, d applied to c5 sine of 2t. The derivative of that would be 2c5 cosine of 2t. There it is. Don't think I need that parentheses there, but there it is. And then d applied, we'll do the negative 4 applied to this is just negative 4 c5 sine of 2t. That's easy. D applied to this would be negative 2 c6 sine of 2t. See? There it is. And then negative 4 applied to that is just negative 4 c6 cosine of 2t equals 0. So look, let's collect up all the terms. The sine of 2t is here, so we need a c2, and it's here, so we need a minus 2c3, right? And it's here, so we need negative 4c5, and it's here, so we need negative 2c6. So sine of 2t times all this is equal to 0. Cosine of 2t, okay, is, here it is, 2c2. Here's another one, plus c3. Hear it? See it? Plus 2c5 here, right? And minus 4c6. And that's equal to 0. So, that gives us a system of equations with our unknowns, c2, c3, c5, and c6. 2 equations, 4 unknowns. So it should have a 2-dimensional solution set. And we can find it using row operation. So here's our matrix. The start, here's the coefficients, 1, negative 2, negative 4, 2, like that, and 0 on the right. And 2, 1, 2, negative 4 here. So we're going to do this row operation, negative 2, row 1, add to row 2. I don't know if you see what the nice thing happens there. That gives us a nice, beautiful 0 here. And then we're going to do 1/5 of row 2. So if we do that, we got 0, 1, 2, 0, 0. Oh, isn't that nice? And now we're going to do one more thing. We're going to do 2 applied to row 2 and add it to row 1. And when we do that, we got this row-reduced echelon form for our matrix. 1, 0, 0, negative 2, 0. And 0, 1, 2, 0, 0. Now, I don't know if you see what this top equation says. I know it's just a row of numbers in a matrix, but really, remember, this is the C2 column. the C2, the C3, the C5, the C6. So this says C2 minus 2C5 equals 0. So C2 equals 2C5. Except for the fact this is C2, C3, C5, and C6. My fault. It's C6. C2 equals 2C6. My bad. The second equation says C3 plus 2C5 equals 0. So C3 equals negative 2C5. Or better written, both C6 is 1/2 C2, C5 is negative 1/2 C3. Well, that is wonderful. So here's the system, the solution with now only three constants. X is C1 e to the 5t, y is, or sorry, X is, I'll say it again. X is C1 e to the 5t plus C2 e sine of 2t plus C3 cosine of 2t. Well, that's what we had before. But what we are able to do now, we're able to replace the C4, C5, and C6 with negative 6C1. That's that we did way up there early. And we just found we replaced C5 with negative 1/2 C3, and we replaced C6 with 1/2 C2. So there is the solution to the system with the three constants as required.
Will this unit always be this complicated?
Well, it might be, but not very many are as complicated as this one was.